Hello everyone, my name is Amanda Bentley and I'm going to be doing a presentation on the photoelectric photometry of the Pleiades. So a little bit about the Pleiades, what is it? The Pleiades is an open star cluster that is one of the closest star clusters to Earth. The cluster itself consists of many hot B-type stars. We'll get into that a little bit in the next slide about what hot B-type stars actually are. According to Galli et al., it is the closest open cluster to the Sun in terms of age and richness. The Pleiades is an important cornerstone in many studies related to star formation, from physical models to observational properties of young stars. Observing the properties of young stars is a little bit about what I'm going to be doing in my lab. I'm going to be observing the age of the cluster itself. Little fun fact about the Pleiades itself: in my culture, it is known as the Seven Sisters. So what are B-type stars? According to the Office of Astronomy for Education, it is a star with spectral type B. Astronomers identify B-type stars by the presence of neutral helium lines along with hydrogen lines in their spectra. So with that said, the neutral helium lines with the hydrogen lines basically says that the star is going to burn extremely hot. And it does. The B-type stars burn in between 10,000 to 30,000 kelvins. From the ground on Earth, we can recognize these stars up in the sky because they are bluish-white stars. A few of these stars are popular in the Leo, Orion, and Virgo. In the Leo, it is known as Regulus, and Orion is the Regal, and in Virgo, it is the Spica star. So getting into my lab, I'm going to be using a simulated photometer. This photometer is going to be able to let me measure the apparent magnitude of stars, and from there I'm going to be able to design an HR diagram to get an accurate reading. We're going to use the relationship between the apparent and absolute magnitudes, and then we're going to use those numbers to calculate the distance to the star clusters, which will then give us our age. So we collected the data of about 40 stars within the Pleiades cluster, and we use that data to be able to find our apparent magnitudes. We have to assume that all stars are the same distance away. The main reason is that we assume that all stars in a cluster formed almost simultaneously from the same cloud of interstellar gas, which means that the stars in a cluster should be very homogeneous in their properties. This means that the only significant difference between stars in a cluster is their mass, according to Penn State. So generally, without the assumption, we cannot consider the impact that it will have on the magnitudes if we don't assume that all stars are the same distance away. So after collecting the data of about 40 stars to find the age, we are given the B and V values, our absolute and apparent magnitudes. We subtracted the B value from the V value in order to create our HR diagram. So then we have to adjust our M minus M and then our E, B minus V in order for it to be able to line up with the cluster on our HR diagram. Using our M minus M value for the formula as given, it gives us 25.12 parsecs. In order to find the age, we have to look where the sequence started to turn off, which is known as our MSTO, which is around 0.1. A 0.1 is the equivalent of an A5 star, and A5 stars generally have the mass of 2.0. So the formula to calculate the age is given, which gives us 1.77 times 10 to the 9th years old. So here's my HR diagram on the left here. The yellow triangles are our EB minus V and our M minus M, and those are our adjusted values in order to be able to find the median between the star cluster. The individual stars in the cluster, the 40 stars, are the blue squares that you see surrounding the yellow and pink triangle and square there. So our M minus M is over 2.0, and our EB minus V is around a 0.2. So as I said earlier, we had to adjust our M minus M so that the yellow triangles are lined up, and our 0.1 is our MSTO, right around where the sequence started to turn off at. So given our age of 1.77 times 10 to the 10th times 10 to the 9th years old makes sense. Although our data could have been skewed a little bit because we did collect this data over a period of 2 different days. The lighting from the sun is different both days, and the data was taken at 2 different times. What also could have affected our data is that we had to assume that all stars were the same distance away, which also impacted our results. Although, when comparing it to other students, our graphs and data do look alike, so I don't believe that our data could have been skewed off that much due to taking it over 2 different days. And here's my works cited. Thank you.